Okay, so what we're going to talk about today is why is it that a block on a spring system is an example of simple harmonic motion. So in other words, it moves in a sinusoidal fashion. How can we prove that that's exactly the case? So we're going to really dig into some pretty heavy-duty mathematics here in order to explain this. And this is something that in AP Physics C, it's not something that you typically need to do to make the proof. But I think it's worth taking a look at and seeing, and then realizing that if we understand how this model works for a block on a spring, we can also apply it to lots of other different systems. So we've talked about the idea that if you have a block attached to a spring on a horizontal frictionless surface, you have three forces acting on it. So you have the weight of it, you have the normal force acting on it, and you have the spring, which is trying to restore the object to equilibrium. So we talked about the idea of a restoring force. And if that spring is an ideal spring, then the restoring force is equal to, has a magnitude of kx, and it points back towards equilibrium. So if I apply Newton's second law to the x direction, I get ma in the x direction equals the net force in the x direction. Ma becomes negative kx because the displacement from equilibrium in this picture is to the left, but the force is to the right. So they are opposite in direction. That's where the minus sign comes in. And so the acceleration is equal to negative k over m times x. So really what we have here is a constant, a negative constant that is, negative constant times x. But keep in mind, as the object moves from left to right, x is going to change. So this acceleration is not a constant acceleration. So we can't use our typical equations of kinematics for constant acceleration to describe this. This is going to be some sort of differential equation that we're going to have to solve in order to figure out what is the position function that describes this scenario. Okay, so first thing to recognize is that x and a sub x are related to each other, right? If we think about it, x is the position of an object and a is its acceleration. Well, the acceleration is the second derivative of position with respect to time. So I'm going to rewrite this function, this differential equation, I should say, this way. I'm going to say the second derivative of x with respect to time, that's the acceleration, is equal to negative k over m times x. So this is a differential equation because x is related to its second derivative. In fact, this type of differential equation is called a second order differential equation, and there's lots of different types of second order differential equations that if you study physics and math more carefully, you'll learn to categorize and so forth. Okay, so basically what we're looking at here is we need to understand that x of t is a function. We're not looking for a value of x. We're looking for a function, x of t, that satisfies this differential equation criteria. All right, so you need to think about it like this. What it's saying is there is some function, x of t, such that if you take its second derivative with respect to time, you get the same function back, but times a negative constant. That's basically what this expression is saying. Okay, so if you just think about what do you know about calculus, what function, when you take its derivative twice, gives you the same function back? Well, it's certainly not going to be like a polynomial function, like a quadratic or cubic function or something like that. That's not going to work. All right, if we take the derivative of those things, it doesn't give us the same function back. All right, you might be able to see that this function is either going to be some sort of exponential with e to the x, or it's going to be some sort of cosine or sine function. But we're going to basically go and prove all of that. All right, so I'm going to write it like this for now. This is what I want you to think about. Think about it as an exponential. I'm going to say that there is a possible solution, and that possible solution is x of t is some constant, I'm going to call a for now, times e to the r times t. All right, now think about that just as a possibility. If we took its derivative, right, if we take the derivative of x of t, we would get v of t. And if you take the derivative of a times e to the rt, the r comes out in front. This is chain rule. So we get r a e to the rt. And if I take the derivative of that again to get the acceleration, I would get r squared a e to the rt. So if you look at this and you look at this, you notice that that original function is in this expression with a constant out in front, if we assume that a is, or r, excuse me, is some sort of constant. So this is a possibility for our particular situation that we're talking about here for our spring. Okay, so what I'm going to do first is I'm going to rewrite, just copy down our expression here. And I'm going to do kind of a funky substitution here that is not really going to make sense to you when we first do it. It's not going to make sense until later on in the chapter when we start to make some connections to some other types of motion as to why did I pick this particular constant. But what I'm going to do is I'm going to let k over m equal omega squared. I know it looks like w, but let it equal omega squared. Like I said, it's not going to make sense right now as to why did we call it omega squared, why didn't we call it like b or c or k or whatever. But later on, that'll start to make more sense. So we can rewrite then like this. Negative omega squared x. Okay. Now, let's apply our possible solution that we came up with earlier, this a e to the rt. Let's try that in this particular situation. Okay. So if you look at when we did this possible solution and played around with that, you notice that we have r squared times the original function equals the acceleration. And if you look at this specific example here, we have negative omega squared times the original function equals the acceleration. So just map those two things. The second derivative of x with respect to t is the acceleration. X is a times e to the rt, and r squared is negative omega squared. That's what you can see from mapping this out. So r squared is equal to negative omega squared. Okay, so if we took the square root of both sides, what we're going to end up with is that r equals plus or minus I omega, I being the imaginary number. All right, so if we do square that, we'll get, I squared omega squared, which would be negative omega squared, because I squared is negative 1. Okay, so if we use r equals plus or minus I times omega, we can write our function like this. X of t is a times e to the I omega t. because we had a e to the RT in our model from earlier. All right, so this function right here is a solution to this differential equation. Okay, but we're going to take it a little bit further. It's a pretty interesting thing here. So there is an identity called the Euler identity that says that e to the I theta is equal to cosine of theta plus I sine of theta. All right, and the reasons for that are pretty complex, and hopefully we'll be able to take a look at, where does that come from and how does that work. But for right now, just take it for granted and assume that that is true. All right, so in our case, if e to the I theta is cosine theta plus I sine theta, then in our case, a e to the negative I omega t, all right, in our case, is going to give us a times cosine omega t plus I sine omega t. So a times the quantity, cosine omega t plus I sine omega t. All right, so this first part, a times cosine omega t, is a real solution. This second part over here, a times I sine omega t is an imaginary solution. So this imaginary solution doesn't exist in reality, all right? In some other instances, when we're talking about electricity and magnetism and things like that, using this imaginary solution actually does have actual benefit, but for our purposes here in mechanics, only the real part of the solution is actually useful. So I'm going to reduce that and say that x of t is a times cosine omega t. So it is a sinusoidal function, okay? And if you want to check that, check it by taking its derivative. The derivative of x would be velocity, and the derivative of a cosine omega t would be, think about the chain rule, you would take the derivative of what's inside and bring it out in front. So we have omega a sine omega t, all right, and with a minus sign. And then if you take the derivative again to get the acceleration, again, you're going to take the derivative of what's inside there. You're going to bring the omega out in front. You're going to get negative omega squared a cosine omega t. Take a look. This is the original function. You're multiplying it by negative omega squared, and you're getting the acceleration. That's exactly what we said up here when we did the differential equation. All right, so this checks. It works. Now, to make it a little bit more generic and deal with situations where maybe the object doesn't start at its maximum position at the origin, what we're going to do is we're going to just expand this a little bit and say, instead of x of t being a cosine omega t, all right, think about what that looks like, right? At time 0, this thing would be at its maximum position, because a cosine function starts at 0 degrees or 0 radians at its maximum height. Okay, so this would be at its farthest position from equilibrium at the exact time when it starts. Okay, in reality, that might not always happen. All right, maybe you take an object on a spring and you pull it back and you release it, but you don't turn on the motion detector until a few seconds later. All right, so to deal with that sort of situation, we can write it in a more generic fashion, like this: a cosine omega t plus phi. And phi is just a phase angle that what that's going to do is just shift the graph to the left or to the right to make up for, if the object doesn't start at its maximum position. Okay, so this is a pretty complicated proof, but it shows that an object attached to a spring does, in fact, move in a sinusoidal fashion. And, when we do this in an experiment, we will see that this is exactly true, all right? When we actually hook up a motion detector to an object and we allow it to oscillate using a spring, we're going to see that it maps out as a cosine or a sine function, just like it's predicted here mathematically. And so that is the solution to this differential equation that we started with at the top. And what I want to really impress upon you is that basically anytime we end up with an acceleration that's proportional to the position with a constant in front, the math's always going to work out the same way, and we're going to always end up with some sort of cosine or sine function that describes that.